Okay, welcome back everybody. We're going to talk about alternators today, and we'd like to look at a standard alternator that has a fully self-contained unit. And one thing to remember when we're dealing with alternators, that essentially what you have is an AC output, but in order to get an AC output, we have to be able to generate some sort of a DC current inside to provide a field, and that's done using essentially a DC generator. Now, what we have on the screen here is we're looking at a self-contained unit, and you can see that over here what we essentially have is the DC generator. And if you recall back to when you took generators, we have a field and we have an armature, and it's that exciter field that provides the residual magnetism with a north and a south pole here and here, so that when we turn the exciter armature through the field, and you can see your exciter armature is right here, when we turn that exciter armature through the field using a mechanical force, it's going to cut across the north and the south pole, which in turn will generate a voltage causing current to flow. But the most important part of this particular slide is just to demonstrate that we have two units. So again, we have this right here, and that is really our generator, and we'll write that down here. And it's that generator that will in turn is going to provide us the current that's necessary to produce an AC voltage. So if we split this unit in half, we could do that, and that's our generator. Now when we go on the other side here, we have our alternator, and your alternator is where we're going to produce our AC output, and that's essentially how AC is produced on our power lines, and that's what powers buildings and houses and so on. So there's two parts to it, but it is one self-contained unit. You will also notice that the prime mover, and that prime mover could be a wind turbine, it could be a water turbine. We might be using nuclear or coal power to turn this rotor, and when we do that, the entire rotor in here, this whole thing, is what turns, and it does it all at the same time. So clearly you can see that it is a self-contained unit. Now we're going to move on to the next. So we want to, this here is a real life picture rather of a generator, and again you can see we have there's our generator part, and that generator is what produces the DC current that we're going to pass through to our AC part, which is right there. So there's our main AC alternator. So again, we could split this in half, and everything on this side is your generator, and everything on the other side then is your alternator. So that giving you an idea of what it actually looks like, and this is a fairly big machine. Alright, let's take a look at what happens when we start making this thing turn. So first of all, just remember your prime mover down here is turning the entire portion of the rotor, and your rotor consists of your alternator field, and which has your rotating rectifier, and that also includes the exciter rotor, which is your armature of your exciter. So that whole thing is turning via wind, water, nuclear, what have you. So just keep that in mind as we go through this. So again, I'm just going to keep our drawing clean here. See if we can erase this. There we go, that's nice. So in order for this thing to work, now at this point you guys, we have no load attached at the alternator output over here. There's nothing attached. All we're going to do is look at where current flows once this thing starts turning. So right now at this point, the prime mover is going to bring up the rotor part of this machine up to rated speed. Now, there's only one place for current to flow in this machine with no load attached, and that's going to be this way to the brushless exciter. So current starts to flow this way, like so. And remember, this is AC current because we're connected to the same 2 points. If you look back over here, these same 2 points are essentially the 2 points all the way across to the alternator output, meaning we have an AC current flowing. Now, we come in with AC current to this full wave bridge rectifier right here, and of course its job is to convert AC to DC. So we get a rectified DC, and DC current now flows out to the exciter field. In order for us to start to build up a voltage over here at our output, what had to happen first of all is there had to be residual magnetism due to a small, fairly weak north and south pole that it should be existing on the exciter field. If there is no residual magnetism, clearly we're not going to build up, or there's a chance we won't build up. So we're assuming here that we have some residual magnetism in that north and south pole in the exciter field, which you'll notice is located in the stator. Again, this is not a big part of the machine. When you look at the overall alternator, it really is just the bell end of it. It doesn't take up a lot of space because we're not going to be passing much current through the exciter field as compared to the alternator. So the exciter field has low current but many turns of small wire to give us the ability to produce that nice big strong electromagnet to excite our rotor. So at this point, current is flowing through our exciter diodes, creating a bigger north and south pole, which of course gives us our lines of force in here. And as this prime mover turns the exciter rotor through those magnetic lines of force, that induces an AC voltage onto the exciter rotor. That AC voltage then, which is essentially an electrical pressure, is going to cause AC current to flow out to our rotating rectifier. And remember, this rotating rectifier is physically part of the machine. It's built right on the rotor itself. There are no brushes here whatsoever. So that AC current goes to our rotating rectifier, which is rectified by what kind of rectifier? Well, wouldn't you know it, we have a three-phase full wave rectifier, which will provide a nice or relatively clean DC output, which now means that current will flow to our alternator field. Now, unlike the exciter, the alternator field is located on the rotor. So our north and south pole for our field are actually part of the rotor that's turning, which is the opposite to what we had in the exciter, where the exciter field was actually in the stator. Doesn't matter where they are, and as we've discussed in class, the bigger machines or anything over about 1 kVA or 1,000 volt amps is usually means we have a rotating field in our alternator. So now we have these magnetic lines of force that are turning at rated speed, cutting across our alternator armature conductors. Now the alternator armature conductors now have a voltage induced in them because we have relative motion between a magnetic field and a conductor. So we now produce a voltage at our alternator output. The amount of voltage that is produced at our alternator output is dependent upon a few things. We could look at the number of turns in the alternator armature. If we were to increase the number of turns, we would increase the amount of induced voltage. If we were to change the armature core in the alternator, something that is more permeable would produce a higher output voltage. And the third variable that we can take a look at would be to alter the amount of the strength of the magnetic field in the alternator field. So if I had a stronger north and south pole that was rotating, that also would induce a higher voltage in the alternator armature. Realistically, the one thing we can control is the strength of the magnetic field in the alternator. So our alternator field is really the only variable that we would realistically control, and we can do that through what's called a voltage regulator, which we will discuss in class, or I might even provide another scribblecast at some point to take a look at that. But hopefully this gives you an idea as to how this operates. Now that we've produced a voltage at our alternator output, and we have not yet connected load, we have to talk about a couple of things, and that is the voltage drops that occur internally on any machine, including in this case an alternator. Now, understanding, if we go back to our formulas and we look at voltage is equal to our current times our resistance, we know that anytime we have zero current flow, that means we have 0 volt drop. So when no current is flowing, in this particular case, we know that there is no internal volt drops. Now, there are several volt drops that occur in an alternator. We have a volt drop due to the resistance of the actual windings inside. We also have a volt drop due to our inductive reactance inside this machine. And also, if you recall, we also have a volt drop due to armature reaction. And that armature reaction is due to the distorted magnetic field. Now, none of this happens, none of these voltage drops happen until we have load attached and current starts to flow. So just remember, whenever we're talking about alternators and we're looking at the alternator output, and let's use an example here, and let's assume that our alternator output is 120 volts AC, which is a pretty standard voltage that we use in our houses. So the idea being is that in order to produce that 120 volts, we had to generate a little bit more than that, because we have, as soon as we connect load, so if I actually connect some load here, and we come out and let's connect some sort of a load, there's just showing some sort of a resistance, and then let's put an amp meter in there to measure current. And so we already know then that my voltage across the load here, that voltage we already know is going to be 120. Neglecting any resistance in the lines, we're really measuring for the most part at the same point as where we would measure at our alternator output. So now we've connected load and current is going to flow. Now that current is flowing, we are going to have some internal volt drops. So the internal volt drops, one of them clearly is the voltage dropped across the resistance of all of the armature conductors. The other one is also voltage X sync. Now that stands for synchronous reactance. Synchronous reactance is the combination of voltage due to armature reaction, which is that distortion of the magnetic field, and voltage due to inductive reactance. Remember, this alternator armature is a coil. Anytime we have a coil, it has the property of inductance, and inductance is the property of an electric circuit that opposes a change in current. So when we take our voltage drop across the inductive reactance and our voltage drop due to armature reaction and put them together, that combination is called voltage synchronous reactance, and that's represented by X sync, which is this guy. So when we take basically our entire voltage drop due to our in-phase component, add to that the voltage drop due to our entire out-of-phase component, and add to that our terminal voltage, that gives us what we were required to generate in order to get the terminal voltage. So in this case, let's just say that our voltage due to resistance drop was 2 volts and our voltage drop due to synchronous reactance was 4 volts. The question is then, if I was to maintain a full load output at 120 volts, assuming that we're at full load right now with the load we have connected, that would mean that I would have to produce a total of 126 volts in order for me to have 120 volts on my output. Kirchhoff's voltage law says they have to add up. That's his formula. That's what he's indicated. And when we add up our voltage drops at their angle here, all of these need to equal 126 volts. So our terminal voltage, which is where we connect our load, is going to be 120 volts. We have 4 volts dropped across the out-of-phase component, which is the combination of armature reaction and inductive reactance, and we have 2 volts dropped across the resistance of the windings internally, for a total generated voltage of 126 and 26 volts.